Okay, so it's time to begin. I just want to alert everybody, make sure everybody got the email I sent out. If you didn't get it, just go to your Compass. And it says that, as you know, we delayed the due dates right here. Homework 7 and homework 8 have been extended. So tonight, homework 7 is due, and then Thursday, homework 8 is due. And now there's this exam 1 conflict sign-up that is posted online Kappa, and anybody who wants to can take this conflict. All right, the regular exam is at 7 p.m. That's in the evening, and you're going to get your room assignments after I see how many people sign up for this conflict. You'll get your room assignments, and the conflict's the same day at 4:30. And both exams are 90 minutes, and they're basically the same exam. One's not harder than the other, okay? And so by this Friday, you should, if you want to take this conflict, and anybody who wants to can, sign up by Friday, and then both exams are here on the 20th, on a week from this coming Wednesday, and our regular exams are at 7 p.m. and the conflicts are at 4:30. It says, see the exam schedule. So we can go to the exam schedule here, and here it shows you when the exams are. So you know where the conflict is right now, and I'm going to post these locations. There's 4 different rooms. They're all on the south side of campus, but I have to see how many people sign up for the conflict before I can decide the room assignment. So I'll post these on Saturday after I see how many people sign up for the conflict. So any questions on that? All right, and now let's go to our calendar here just to make sure. We just looked at it before, but I just want to show you again here. Okay, and now people who are watching this, you know that you can watch these lectures. Everybody can watch these lectures. So if you miss class, that's what you should be doing, or if you just want to review something. So right now, we're going to try to cover, we're going to cover the two-sample Z and T, and maybe even a little of that. I'm not sure. And I'll try to post right now. These 2 are posted. I'll try to post this one after class. Even though you won't be able to do it yet, some people like to get a head start on it. All right, so that's where we're at, and let's go to the document camera then. Okay. So now this is the last thing we did. It was the one, we're doing these significance tests, and the last thing we did was the one sample T-test. And it was, we had a small sample of only 16, normally distributed population, and an unknown SD. So we make this adjustment where we do this, for all our statistics, we take some difference between what we observe and what we expect under the null. So under the null, we expected the class average to be 70, but we observed a 75. So we see this difference of 5 points that landed 5 points away from where we expected, and we want to know on some distribution, this one's a T distribution, of how unusual that is. And if it's very unusual, we reject the null. All right, now the adjustment we made with the T, because we had a small sample, is 2 things we did. We're going to use these SD plus, where we make our sample SD just a little bit bigger by a factor of what? We had a sample size of 16, so it's a fact we multiply by the square root of n over n minus 1. We're making it bigger, so put the 16 over the 15, right? And so we made it a little bit bigger. And then we compute a standard error for the average based on that. That's what we did. So we have this 5-point difference here. We want to know how many standard errors is that. So we say SD plus, sorry, it's a little bit messy, that's our 12.39, divided by the square root of n, right? And that's what we got. But I just want to show you there's a faster calculation if you want. Like you can do the SD plus. This is what we did. We said right here, 12.39 over the square root of 16, right? But can you see that what that simplifies to? This is SD plus is that, and if we, multiplied the denominator, divided the numerator and the denominator both by square root of n, we'd get, the square root of n's would get eliminated, and we get that. And that's an easier, maybe some of you would prefer to do that. So this calculation would be what? You just take your regular SD12, and instead of dividing by the square root of 16, you divide by the square root of 15. Those two things are equivalent, so you could do, these are equal to each other. So you could do this one or this one. All right? So SE plus average is equal to, you can do SD plus over the square root of n, that if you prefer, or I think it's sometimes faster to do this. They're the same thing. Okay? All right, so that's going to come in useful. It's an easier calculation when we do the two-sample t-test, where we're going to have two samples instead of just one. But first, let's do the two-sample z-test. All right, so the two-sample z-test, what is that? Well, so far we've just been looking at one sample and comparing our what we get in our sample to what we'd expect under the null in a larger population. But what if we have two samples? And that's much more common. Like you might want to compare a drug, the average, a drug to a placebo, a treatment to a control, or you might want to compare males to females, or Republicans to Democrats. So we have two samples. All right? So now it's going to be, if we have two samples that are independent from each other, then we get a very similar statistics. We get our observed difference between the two samples minus our expected over a standard error for the difference. So, and usually the null hypothesis, if our null hypothesis is that we think the two populations are the same, like the null for the treatment and the control group, a drug and a placebo, would be that they're the same, that the drug didn't work any better than a placebo. So then our expected difference would be 0. And for this class, that's generally what we're going to do. So this is usually 0. Expected difference is equal to 0. In the examples that you're going to see, it doesn't have to be, but in the examples that you're going to see, it will be. And so it just boils down to that. So we have this difference between the two samples, our observed difference that we see in our samples when we expect 0, over a standard error for the difference. So let's just remember, like for example, when we had the one sample, we had a one sample z-test where where the professor, I think it was back, the professor claimed that the ACT scores of a university was like right here. This was back on page 71. Okay, where he made, this is the one sample. The null was the professor made this claim that in the population the ACT was really 30. We thought it was less. So our sample S was 29.1, and we took that difference, that 0.9 difference there, and divided it by the standard error for the average. But now let's say you have you wanted to compare ACT scores of males versus females in the population to see if they're different or to see if one performs better. Okay, so we can do an example like that. Let's do it with IQs, okay? So how do you compute the standard error? So let's just take this example where we have the IQ scores in your question, and you might want to know, might want to compare males and females, okay? So the null would be that, so you'd have this whole population here. This would be the male population, whole population. And then you'd have a female population. Now you have, so you're sampling from okay? And I think I'm going to try writing with this instead. So you're sampling from, you have millions of tickets in each, one for each male and female, let's say in the US population, right? So you have millions of tickets, and and we don't know what the average, what the population average is for males. We don't know that, and we also don't know what it is for females, okay? And we also don't know, this doesn't look as good, I can tell already. And we don't know what the standard deviations are either. So we don't, these are unknown. And our null is what? We don't know them, but our null is H naught is what? That in the population, they're the same, right? We don't think there's any difference, but we're going to test that. Let's say some people think males do better on IQs tests. Some people do think that. So let's just, if we wanted to test that, so this is our null. And then our alternative could be that males, some people think they would do better. So we want to know if that's so. All right, so what would we do? We're not going to take the IQs of everybody, but let's say we took a random sample. Let's make it really simple. So let's say we took, randomly took sample size of n equals 25 for both. And it's going to be without replacement always. And then let's pretend, let's say we got a difference in our sample. So let's say our x bar here, our sample statistic right here, our average for the males, let's say that was 102 with a standard deviation of, let's say, 4. And let's say here, no, a standard deviation of, that doesn't make sense. It's about 20 or something. IQs would vary about 15, 20 points. Okay, so here, and we get here an x bar, let's say it's less, 100. And let we say we get some other standard deviation here. Let's say it was 15. So this is for the, that's how, okay? So that's the standard deviation in our 25 numbers. And here we had a standard deviation of 15 in our 25 numbers of IQs. All right, so now what do we want to do? So now we'd have to compute a standard error for each of these, right? A standard error for the sample, for this average for the males, and that's going to be SD over the square root of n. So we'd get what? 20 over the square root of 25. So that would be 4. And here we'd get the standard error for the average for the females. And that would be what? 15 over the square root of 25. So that's 3. So there's our two standard errors. And now we want to know, okay, so what's our z statistic going to be? Our z statistic right here is going to be what? Our z statistic would just be the difference here that we observe, 102 minus 100, that's our observed difference, minus our expected, which is just 0 under the null. We don't think there's any difference. We think they're the same. And now we have to do this standard error for the difference. That's what we have two sources of variation. Basically, when we expect to get, we get 102 plus or minus about 4, and here we're getting 100 plus or minus about 3. So how do we combine those two sources of variation? Well, you know it's going to be, you have two sources of variation, so it's got to be bigger than the biggest one here. It's got to be bigger than either one of them, because now you have variation from two places. But can we just add them together? No, we can't. These are standard errors, standard deviations, but they don't sum. We could add their variances together, right? If they're independent, we saw that already. So, but for the square roots, we can't. But if we add, so instead, what do? So we get this difference of 2. So the square roots are, we take the square root of the sum of their variances, their squares. So that would be 4 squared plus 3 squared. It's like, this is the formula right here. And the proof for this, I just gave you I didn't really give you a proof at all. This is on page 230, and I recommend that you look at it because I tried to write it as simply as possible, and it's basically the square root law, and it comes up a lot. So you don't have to look at it, but if you want, if you're interested, I wrote it in a way that's very simple, and I think people can understand. Okay, so basically, it's the Pythagorean theorem right here. That, like it would be, this rule is like the Pythagorean theorem. You can think of it as one standard error is 3, the other is 4, And when you sum them together, it's 5, right? 3 squared plus 4 squared is 5 squared. It's not 7. So you get the square root of 3 squared plus 4 squared. That's going to be what? That's going to be 5. 3 squared plus 4 squared equals 5 squared. Okay? So that's 2/5, which would be 0.4. And that would be our z-score. And I hope you know, could you see right away that what would we need to reject the null? We'd need, at 5%, we'd need a much bigger z-score than that, right? To just get 5% in that tail, we'd need 90% in the middle, which would be a z-score of like 1.65 or something. But we only have 0.4. So let's look up where 0.4, if you wanted to compute the p-value, I don't have room here, but if you want to compute the p-value, you'd go down here and you'd say, okay, as a z-score, we got a 0. As an expected difference of IQ differences, we'd also expect 0, right? Now we got 2 points, a 2-point difference on here, and that's the 2 points, and now we see that a 2 points is not 2 z-scores, it's only 0.4, okay? So here it would be 1, 2, -1, -2, and 0.4 would be somewhere around here. So that's z equal to 0.4. And that's where our 2-point difference is. That's where it lines up. And you know, in order to be significant at 5%, we'd have to go way far out to get 5% in that tail, which would be 5% in the other and 90 in the middle. So let's first see what a middle area, what we have. Let's first see what this p-value is. It's certainly too big to reject the null. So let's get the middle area for 0.4. Sorry. Okay, so the middle area, and so nice with z, there's just one z curve. So we go to 0.4 and we get 31. Now, if we wanted to reject the null, we'd have to go to get 5% in the tail, which means we'd have to have 5% there, 5%, 90% in the middle, which would mean we'd have to go all the way out to 1.65. That's called a critical value to reject the null. That's called the critical value of z. That comes up a lot. We saw it for confidence intervals. So we're not close to that. Our z is only 0.4. So you keep that in mind. You need a z of at least 1.65 to reject the null. So if you see only a 0.4, you're not going to reject the null at 5%. And we have 31 in the middle. So this is 31% in the middle, which means that we have 59 together in the two tails. 59 together in the two tails. So you divide by half, and that's 29.5 in that tail and 29.5. And that is our p-value. And that's a big p-value. We'd need to get out to right about here, 1.65, to reject that. We'd have to get a much bigger difference. Okay? Now this formula only works if the two samples are independent. What does that mean? It means that when if you took an error from here, plus or minus 4, right, that's not going to influence what happens over here. If it did, if it said, oh, I gave you, this ranges between plus or minus 4, I gave you positive 4, then I'm going to give you the biggest positive 3 over here, then you'd always get, only a difference of an error of 1. Or let's say it went the opposite way. Let's say if they're dependent, if you took a high 1 from here, 4, then you'd get a negative 3 from here. Then you'd have a difference of 7. But they're independent from each other, and that's important. So whatever you get on any particular draw, positive above or below the average, doesn't affect whatever you get on any particular draw here. Does that make sense? Okay. So now that's the idea. And we're going to do this, we're just going to make us, what we're going to do in this hour is we're going to do, I'll show you how this works. And then we're going to make a slight adjustment when we do a t-test. And this, we can also do this for percents. And I say here, when comparing two population percents, the null hypothesis is the percentage of ones in the two boxes is the same. Like here, it's not necessarily that they're the same. They could be different, but once you say the percents are the same, the sigmas are the same. So, so generally speaking, they pool. They take a weighted average of the two sample standard deviations. So based on this pooled, you average the two pooled percents, and then you get the same standard deviation. We're not gonna do that. It's just a slight adjustment. I think it's easier to just keep it all the same for this in the beginning. So we're just gonna do exactly the same thing when we do percents. We're not gonna make a pooled adjustment, but later we will. So we're gonna compute pooled SEs, so I'll just say later. In the next, I guess on page 112, which isn't going to be on this exam, we'll worry about that. We'll compute what's known as pooled standard errors. But right now we're going to assume they can both be, we're just going to do estimates by having them be different here, just basing them on their samples. So don't worry about that now. All right, now let's see what we're going to do. So let's do our example here. So you're going to see these two sample z-tests way more often. Whenever you see a clinical trial, yeah. Go ahead. On the other page, what? The p-value right here, why don't we write this down? So our p-value here, how do we get the p-value? Our p-value is 100 minus the middle area. 100 minus 31, right? Oh, no wonder. I was saying the wrong thing. No, I'm so sorry. 100 minus 31 is 69. I think I said 59. I did. Thank you so much for correcting me. Especially because these are going out to lots of people. I really appreciate that. Yes, of course, this right here is not, this is 69, right, for the two tails together. And then I just want one of the tails, so I divide by 2. And that's how I got the 29. Oops, the 30. Sorry, 30. This should be what? 34.5, right? Thank you. Wow, great. Did everybody else see that too? Did anybody else see that? You get an extra credit point on your exam. Let's do that, because it would be great if you guys correct me if I make a mistake like that, a careless mistake like that. So now this, they have to add up to 100. So this is going to be 34.5, right? Okay. And that's our p-value. Any questions on that? Okay. So now, so the conclusion is, what's the conclusion? We cannot reject the null, right? Because there's not enough evidence at all. It's easy. It looks like this is just a small difference that could easily be due to chance. P is not small enough. It's much bigger than 5%. So this would be, we could never, this looks like, you know, this difference could easily happen by chance. Okay? Does that make sense? And thank you so much. You know, sometimes it's hard to catch your own careless errors. So I really need your eyes. I appreciate it. All right, so now we're going to do another study. We're going to look at a study, and as I said before, that in these journal articles, often you'll see these two sample z-tests because they're comparing a treatment and control. So here's one from the New England Journal of Medicine, and it compared these two diets. This diet, Atkins diet, was very popular. It was a high protein diet, and you could eat as many calories as you want if you just it was all protein, and no carbs, fat and protein. And the other one was a low calorie, the traditional low calorie. So they compared these two diets, a low carb, high protein, high fat diet, to the conventional high carb, low fat, low calorie diet. And so these were 63 obese men and women, and 33 people were randomly assigned to Atkins, and 30 were randomly assigned to the conventional diet. So what we're going to do is we're going to assume that people are chosen from a population of thousands of people wanting to lose weight. Okay? So we have these two samples. There's like, we'll have this, all the people who could have gone on the Atkins diet, and all the people, millions of people, or thousands, however many people, probably millions, who wanted to go on the low-cal diet. If we put them all on the low-cal diet, what would happen? And put all the people who wanted to lose weight on the Atkins. Okay? So, so here's the Atkins null box. And here's the usual low-cal null box. And in each, there's millions of tickets, or thousands, I don't know. Let's say they chose from a pool of thousands of obese people. Okay? So after 3 months, the Atkins group lost an average of 6.8% of their body weight with a standard deviation. This is for the Atkins. And the low calorie lost only 2.7% of their body weight. All right. So that looks like a significant difference. That difference of 4.1%, is that big or small? Now, could this difference in weight loss be due to chance, or did the Atkins work better than the low-cal? So, all right, so the null hypothesis is always that they're no different. So here, even though these say percents, this isn't zeros and one in this box. On each ticket is written what? Not a 0 or a 1, but a number, a weight loss percent. So these are really, it's not a percent problem. It's not a 0-1 box. It's an average problem. It's mu is equal to, from the Atkins, we don't know, and mu for the low-cal, we also don't know. So don't get deceived by that percent sign. Just like you might get an exam score back that says 95%, but that, or, you know, if I looked at all your exam scores, I wouldn't have a 0-1 box. Okay? So this is, and so then we also have a sigma we don't know for both of them. Okay, so that's what it looks like. And then our null is always that these two averages are the same. So we have mu for the Atkins and the low calorie is the same if everybody, if all the people did. In our sample, we happen to see this difference of 4.9, but that's just small and due to chance. That's what the null says. And what does the alternative say? The alternative says, could it be due to chance? So this is right here is H due to chance. That's H naught. And we're going to look, later we're going to look at something called a one-sided, a one-tail and a two-tail test. So let's think about what our alternative here. Did the Atkins work better? Okay, so they think the Atkins work better. So this is going to be our alternative, that the average weight loss in here is greater than the average one in here. Now, if it said we just thought they were different, we knew, but we weren't sure. We know they're different diets, so we expect them to have different, but we don't know if it's going to work better or worse than the traditional. Then we're going to have a not equals. We'll have a not equal sign here. We'll look at that in a minute. But first, let's just do it according to how they did it. Okay? So we set up the box model. We have, we have the null and alternatives. And now what are we going to do? So now we've got to come up, we're going to do our two-sample z-test. gotta put my jacket back on even though I'm hot because my microphone's tangled up in it. Excuse me for just a minute. Oh. See if I can get it out. Okay. So now we're set. All right. So now how many people did we sample from each? Okay. So where's that information? 33 and 30. Okay. This was a very important study that a lot of people looked at the time because a lot of people are on this diet. So now we have, here we have n is equal to 33, and of course it's without replacement. And here we have, we randomly draw from here 30 without replacement. Okay, now what did we get? So our x bar here for the Atkins is 6.8. We don't have to worry about the percent. It's not, it's just a symbol there. And our x bar for the locale is 2.7. So that is our 4.1 difference that we're wondering about. So we know that we're going to have, where are we headed? Let's just think we're headed. Sometimes you can lose sight of where you're going. Okay, so we're going to be doing this z statistic down here. That's going to be our test stat. Our test stat is going to be this z statistic, which is the observed difference minus the expected difference under the null over a standard error for the difference. So this is our observed difference right here. We got that. That's, okay, that minus 0, right? That's just that. And now we're going to do, for the standard error of the difference, what are we going to put in here? We are going to put in the square root of the standard error for the Atkins. I'll say for x bar, that's what we're doing. How much the average is bouncing around with the Atkins. That squared plus the standard error of x bar for the locale. Squared, right? The square root of the sum of the squares. All right, so we know this is 4.1. And we just have to get that. All right, so how do we get it? Well, what is the standard deviation here? We got the standard deviation here. Where do we find it up here? There's so many things. Okay, so that's 5. And the standard deviation here is 3.7. All right, so now, so this is for the Atkins and that's for the locale. All right, so now do you remember? We're not doing a two-sample t. We're going to say this is big enough, 33 and 30. All right, and we don't know the distribution inside there. All right, so now we're going to do the standard error for x bar a. So what's that going to be? That's going to be 5, right? SD over the square root of n, which is 5 over the square root of 33. And I did that, and I got 0.87. And let's do the same thing here. So now we have for this, that's for the average, that is SD 3.7 over the square root of 30. And I got 0.68. So that's our standard errors right there. So that's what we're going to square here. Okay? So we'll get the standard error for the difference here. So that will be the square root of 0.87 squared plus 0.68 squared. Now, what are we going to expect? When we do this, we should expect it to be bigger than 0.87, right? It's going to be bigger than either, like the hypotenuse of the triangle, will be bigger than either one of those, but smaller than the sum. So make sure that's what you get. And when you do that, and I got 1.1, so I got this was equal to 4.1 over 1.1, which is certainly bigger than either one and smaller than their sum. And then that is 3.7. All right, that is our z. So I just want you to know, remember what we said that critical value was what? 1.65. If we got a z over 1.65, we're going to be really far out on the tail, aren't we? Aren't we going to be really far out on the tail? So you can see right now, we're going to reject the null and think, oh, this really strong evidence that the Atkins diet really does seem to help people lose weight more. All right, so, but let's just draw the picture now. So we're going to, okay. So we expect as a z-score 0, and we expect as a weight loss, a difference in weight losses, 0 as well. A difference in weight loss is 0 as well. We got a difference of weight loss of 4.1, and we want to know where to put it on here. And it turns out it's very far up. So this, okay, so as a z-score, we got 3.7, and as a weight loss, this is where the 4.1 is. Okay, that's where it matches up. So now the distance between 3.7 and negative 3.7 is really huge, 99.978%. The reason I'm including all the decimals is because you can see when you get high up, let's look here. When you get really high up into these numbers, I mean, if you just round them, they'll all be 99.9. Okay, so that's why I'm including them all. You don't really need to, I mean, it's so tiny, right? So our p-value is that little speck there. That little speck is going to be our p-value. So our p is equal to what? 100, now I'm going to be careful, minus 99.978 divided by 2, right? So that's 22 divided by 2. So it's 0.011%. That is a tiny p. That's so small. So small. So it's highly. So our p-value is way less than 1%. Remember, 1% is highly significant, so it's very highly significant. It's highly significant. Very strong evidence that the Atkins is better. I don't want you to rush out and do this Atkins diet because it has a lot of other problems, but if you want to lose weight quickly, it's the best. Very strong evidence that Atkins works better. It's a very hard diet for, I would hate it because I love bread and you can't eat bread, you can't eat noodles and all the good stuff. You can't eat carbs. So, but if you want to lose weight fast, it works. Okay. Now, let's go to, remember I just said, all right, your alternative can either be one-tailed or two-tailed. So what does that mean? All right. So which test should we use, one-tailed or two-tailed? So here, as I said before, we use the one-tailed. We only have one tail. But let's say because there was evidence ahead of time that Atkins was better. That's why they were doing it. They were thinking, hey, I think Atkins is a lot better. So they had some idea ahead of time. So they specified. Let's say you weren't sure which was better. You know they're different diets, so they're probably going to have different effects. Well, then you'd put a not equal sign here. And then you don't know whether you're going to get Atkins better or Atkins worse. Which side you're going to be on. So when you do the same exact test, right? The same, but you have to include both tails. Okay? You don't know which, so it doesn't really matter which one you subtract from each other. You just take that pretty much just like the absolute value of that, doesn't matter. And we got 3.7, but if it said not equals here, we'd have to take both tails because, yeah, it landed on this side, but we didn't know that ahead of time. So that's like called data snooping. We're peeking at the data. If we really don't know, we have to take into account it could have just as easily landed on this side because we had no prior knowledge. So we have to take the p-value. We have to double our p-value. So instead of taking the area of one tail by dividing by 2, it would be doubled. It would just be, our p-value would just be 100 minus 99.978. And that's done a whole lot. Okay? So let's read about it here and write that down first. So, okay, so here, this is like the Atkins is better, right? So here, if you say, in our example, we said, okay, so this would be like, I don't know, wherever we put our, let's just put it there. So this would say the Atkins is better. Or we could have said the locale is better. And then we would have fallen on the other side. If we, right here, Atkins is worse. So we would have had the same size tail. So this is the locale is better. If we thought the locale was better, it doesn't matter which direction, it doesn't matter. It's just which way you subtract them. Okay? But then if we thought we didn't know, then we'd have two tails here. So this is, all we know is that the Atkins is not equal to the locale. So then basically, it's really easy to remember because the p-value for a two-tailed is equal to the area of two tails. You get the same z statistic, so it's going to be double. And here, for the one tail, the p-value is equal to the area of one tail. So it's just going to be half of that. All right, so that's what's said here. Both yield the same v, or t statistic, but the p-value of the two-tailed is double the p-value of the one-tailed. So let's say that. So the p-value for two tails, has two tails, is equal to 2 times the p-value for one tail. Okay, so now, which test should be used? That depends on which alternative makes more sense for a given situation at the start of the study, before looking at the results. Remember, you have to formulate your hypothesis before looking at the results. After you look at the data, you know which way the difference went. So it's considered cheating or data snooping to use that knowledge to formulate your hypothesis. If you knew ahead of time, that's fine, but not after you peek at the data. To guard against that, many people in software programs always use two-sided tests. That's why in journals, when they talk about, when they ask you to do a test, they ask you to do a two-tailed test because they're trying to guard against that, because they don't know whether the people looked at what the results and then changed it. Because remember, you want to get a low p-value to reject the null so you can make a discovery and say the treatment worked. But it makes more sense to use the p-value that fits the correct alternative hypothesis, certainly to understand it if you care about, the science of it, and not just. But this is why it's always all the software programs, and when you submit to a journal, they always want you to do a two-tailed, just to guard against cheating. So basically, they're asking you for, it's like changing the p-value to 2.5%, because you have to get, if it's 5%, right? But then you want a 5%, you'd have to get 2.5 in each tail to meet that 5%. Otherwise, it would be 10% significance level. All right, so that's the idea there. So we can do an example. Let's see. All right, so let's do this example. And this is an example with 0, 1 box. Any questions so far? All right, so now we're going to do this two-sample. Now these are 0, 1 boxes, so it's a real percent problem. So this is a two-sample z-test for comparing two percentages. Okay, the other one was for averages. So we're going to have 0, 1 boxes. All right, so 2 0, 1 boxes. Gallup asked a random sample of 500 men and 500 women. This was Valentine's Day is coming up, so this is appropriate. It's on Valentine's Day. They often ask things like this. If they had ever fallen in love at first sight. And to see if 44% of the men and 36% of the women said yes. Is the difference in responses likely to be due to chance variation or not? Perform a significance test. All right, so I should tell you your exam is going to be all multiple choice. So I might ask you what the null hypothesis is. So, you know, and I do it in a multiple choice format. So which of the following is it? Circle it on your own paper to make sure you understand before I do it. Just think about it for a minute. The null hypothesis is always about the null boxes, about the population. Hint, null hypothesis is always about the whole population, not the sample. So we can eliminate that. Eliminate that. Okay, eliminate that. Now, the difference in the population percents is 0 or both population percent. It's this one, right? So here. Both population percents aren't 0, obviously. Okay, now, suppose before looking at the results, you thought men and women would respond differently, but you don't know which direction. Should your alternative be one-sided or two-sided? One-sided and two-sided is the same as one-tailed and two-tailed. They're used interchangeably. Okay? So if you don't know, what should it be? Two-tailed, right? So it should be two-tailed. That's the same as two-sided. You'll see them interchangeably. Okay, now after looking at the results, you looked at the results, and in our sample, we saw 44% of the men said yes. So now, after looking at our sample, should we change to a one-sided or not? No, you can't change to after looking at the data. No. You still have to do the two-tailed. Because that would be cheating. After you look at the results. After looking at the results is cheating. If you don't know ahead of time, that's cheating. It's called data snooping. You're looking at the data before. You're supposed to make your hypothesis before looking at the data to find stuff out. You have to have a hypothesis before, not after you look at what you got. Okay, now we got that, let's say, and now we're interested if it would hold up. Then the next time we do it, so you decide to repeat the survey to gather more evidence to see if men really are more likely to fall in love at first sight compared to women. Now should it be one-sided or two-sided? Now you know more, so you can make it one-sided. One-tailed or two-sided, okay? Fine. So let's do it. All right, so it's exactly the same as what we've been doing. We have these two null boxes, right? One for males and one for females. H naught is what? That the percentage, so we have ones and zeros in each, because it's a yes, no question. Yes, you fall in love, or no, you don't. So that's what I mean by these percent problems. They have 1, 0 boxes, and the percent here, we don't know. And we don't know. We know that whatever this is 1 minus it, but we don't know what they are. Okay. So now we say the percent, we'll call it P. We've been calling it P. Instead of the sample's P hat, the percent is P. P right here for the males is equal to P for the females. The percent in the box is equal. And the alternative is what? For the, do both one-sided and two-sided. Okay. So for the two-sided, It's just going to be not equal. That's the two-sided. And for the one-sided, we were thinking that because we've decided to think it's going to be higher in males. So you have to specify which direction you think it's going to go in. Okay. So now, if we thought it was females, we could say percentage of females is higher than males. So you could get a positive. It doesn't, you know. All right. It's just the size of the z-score. It's just, if we do a one-sided, it's one tail. Now, what do we have? We have millions of tickets in each box. That's one representing every male in the population because it's a nationwide survey. They either said yes or no. And our sample size we're drawing out of here is 500 without replacement, and same here. Okay, so that's what it looks like. And then we get a percent here. We could call it X bar, but people generally don't. X bar is like an average for when you have quantitative. When you just have ones and zeros, they usually just call it it's a percent. So we'll just, it's an average for, we'll just call it a percent, so it's p hat. Okay, that's what we call it. So p hat, instead of p's for the population, p hat's for the sample. So we got a p hat here of 44%, and here we got a p hat of only 36%. So that 8-point difference, do you think it's real or due to chance? That's what we have to get. So now, what are we going to do? So now we're going to get the standard error for both of them, right? Now the standard error for 0-1 box is easy to get just from that. We don't need a standard deviation. We get it directly from the percent, right? So this is the sampling error for the percent of males in our sample. That's what it is. And what is it? We're using this as the estimate of the standard deviation of the box, right? So the standard deviation of this box, a 0-1 box, is what? Remember what you can do? It's 1 minus 0. I'll say this is just going to be SD divided by square root of n times 100, right? Now, the SD, we're estimating it with 0.44. 1 minus 0 times 0.44 times what? If this is 0.44, this has to be 1 minus 0.44. So what is that? Point what? 56 over the square root of 500 times 100. And I did that, and I got, what did I get? 2.22%. Okay? This is going to be about 0.5. And now you can do the same thing here, and you're going to get the standard error for the percent of females. Now here's where let's just do it first. And this is 0.36, right, times what? 0.64 over the square root of 500 times 100. And then when I do that, I got 2.15%. So they're very close to each other. And you know what? Theoretically, you really should be using a pooled estimate, which would be, we'll do that later, but we'd say, okay, if the percents are the same, then their standard errors have to be the same. But they're so close, and it works out to be the same thing. So it's just much easier just to remember one formula for both for this first exam. Okay? All right. And by the way, I'm going to give you, you're not going to have these formulas you're going to have to know, but I'll write a list of them that you really need to know and before to study from. But you're not going to be given formulas on the exam. Okay? So now, what do we have? We have these two. So now we're going to do our z. All right, we're ready. So now we did all this. Now we're ready to do the z. And I think the z is just what? Our observed difference minus our expected difference, which by the null is always 0, over the standard error for the difference. And so what do we get? Our observed difference is that 44% minus 36%. So we know that's an 8% difference. And we just want to know if it's big or small. We have to compare it to the standard error. So we combine these two by the square root of the sum of their squares, and we know we're going to get something bigger than either one of them, but smaller than their sum, right? So it's 2.22 squared plus 2.15 squared. Okay, and so what I got was 8% over this was 3.07%. So that is bigger than either one, but smaller than their sum. And now that gives me 2.59. That's the z-score. See, the percents cancel out, and we just have a pure number. And now you can just see, right, for a one-sided, remember that critical value was 1.65, so we're going to be rejecting the null. For the two-sided, what do you think it is? Two-sided. That means both tails together would have to be 5%. So that would be 95% in the middle. That would be a z-score of 2, and it's bigger than that 2. We'll see that. So let's do it. So let's do it for both the two-sided and the one-sided. All right, so now what are we going to do? So we're going to get our p-value. We draw the normal curve. And here 0 is a z, just so we remember what we're doing. As an expected, as a difference between difference of percents, we'd expect 0. We got 8%. So difference is a percent difference, whatever you want to call it, percent difference, sorry. And now we got way out here. So this is 2.59. That's where that 8% difference is, 2.59. So between 2.5 and negative 2.59 is 99%. So for the two-tailed, what's it going to be? For the two-tailed p-value, if we did a two-tailed test, we get what? So for two-tailed test, it's just 100. It's just 1%. This is 0.5% here, and 0.5% there. 100 minus 99. So there's 1%. But for the one-tailed test, the p-value is just one of them. So it's 0.5%. In both cases, we're going to reject the null. Does this make sense to people? And all we needed, if you think about it, if you're going to do a one-tailed test and want 5%, you don't have to go out to get 5% and 5%. That'd be 90% in the middle, 1.65. But if you want to do a two-tailed test and get significance, that means the 5% has to be distributed between two tails. So you need 95% in the middle. See, that's important to think about when you're, because it comes up a lot. All right, now let's see what we have to do. This is just a summary. All right. A good summary. Now, the two-sample t-test. So let's do a two-sample t-test. These are really common. You'll see these a lot too, because often you have small samples, and you're looking at not 0-1 boxes. Remember, for a 0-1 box, you would never do a t-test, but boxes that have numbers. You're looking at averages. Okay. So in the last chapter, we saw two-sample z-test to compare the means of two populations, or percents, using this. But if our sample sizes are small, and they're drawn from roughly a normal population with an unknown standard deviation, unknown sigma, We just know our sample standard deviations. Then we should use this two-sample. And it's exactly the same thing. We just make that adjustment to the standard errors because we don't know the standard deviations of our population, and with a small sample, our standard deviations of our sample aren't as good estimates. Now, this two-sample t-test doesn't exactly follow any t-curve. This is problematic. So it's hard to decide how many. With the one-sample t-test, the one sample does follow a t-distribution. But when you get to two samples, it doesn't follow a t-distribution anymore. So it's a little bit problematic. It's better than the one sample, but doesn't really, it's better than the z, but it doesn't really follow a t-distribution. So since we're estimating the standard deviations of two samples, the simplest and most conservative approach is to use the most conservative approach is to use this as our degrees of freedom. Okay? So that's what we're going to be using for the degrees of freedom. All right. Now, so let's say this randomized double-blind test was done to see the effectiveness of a drug designed to improve memory in Alzheimer's patients. So now we have this small sample, 20, that's our n. So right away, and then the other one is 16. Those are our two n's. So by the way, our degrees of freedom are going to be what? This is the smaller one. So it's going to be 16 minus 1, which is 15, because this is the smaller one. We have two samples. All right, so 20 took the drug and 16 took the placebo. And then patients were given a pre and a post memory test. They had to recall 15 words, and an improvement score was recorded. So how much they improved between the two tests. Okay, so now we look at it, and the drugs had a mean of 3. They improved by 3, whereas the placebo only improved by 1. They only remembered one more word. So you'd say, oh, that difference is 2. Is it significant or not? That's what we're wondering. Okay? All right. So now we're assuming all these 3 conditions are met. The small, we don't know this, we're assuming that their scores are normally distributed. So now let's look at this. So here, first of all, we have 2 small samples. And this is X bar, and this is SD. Now we could compute SD plus, or we could do it that other way by just taking this when we do the standard error for the average. Let's just go ahead and see what we need to do. All right, so fill in each blank with either equals, greater than, or less than here. All right, so what is our null hypothesis? Do we know whether our null hypothesis is always what? That the drug and the placebo are no different. So this should be what? Remember, this is the null, not the alternative. This is going to always be equal. All right? Does that make sense? All right. And now, suppose you have prior evidence that the drug does work. You think you have prior evidence. Then the difference is going to be what? Greater between the drug and the placebo. Suppose you have no idea if the drug works at the start of the summary, but after you snoop and look at the results, right, you believe it does. Well, then you can't do this. You have to say at the start of the study, you have no idea, so you don't know. You think they're different because one's a drug and the other's a placebo, but you don't know. Maybe the drug's going to harm these Alzheimer's patients and make them forget stuff. Okay, so now we want to compute the t statistics. So what are we doing here? So this is exactly the same. I don't think we have, so let's just remember our logic. We're just doing t is equal to our observed difference, right? Minus the expected difference, and I keep writing this, but the expected difference is 0, so you really don't have to, over the standard error. But now we have to use standard error plus for the difference, and so that's our only. So what is the standard error plus? Okay, so we've got this difference here of 3 minus 1. That's our difference. But how do we get this standard error plus? All right, let's think about it. So we want to get one for each sample. So we have the standard error plus for the drug is equal to. Now remember, we could either do, okay, you could do an SD plus. You could do is equal to SD plus over the square root of n, in which case, if you wanted to do that, I'm just showing you, if you wanted to do that, what would you do? You'd get an SD plus, you'd say 4, now you want to make it bigger, so you'd multiply by the square root of what? The sample size is 20. So is it going to be square root of 20 over 19 or 19 over 20? You want to make it bigger, so it's going to be 20 over 19. And for this one, you take your SG, and again, the sample size is 16. You know it's n and n minus 1. So it's going to be the square root of either 16 over 15 or 15 over 16. Which one? Make it bigger, so it's n over n minus 16 over 15. And you'd get something bigger there. But remember, you could do that, and then you would take whatever you got here, which is slightly bigger, and divide it by the square root of n. But I think it's easier to just use this instead. This is, remember we said it's the same thing as SD over the square root of n minus 1. It's the same thing. So I'm just going to do that instead. All right? So that one's going to be what? So the SD for the drug is 4 over the square root of 19. And then we'll have SE plus for the placebo, which is equal to 3 over the square root of what? 3 over the square root of what? 16 minus 1, which is 15. Okay? Now, the reason I'm going to leave it like this is because, watch, when we do the standard error of the difference, right, we want the standard error of the difference. What are we going to do here? Let's do it right here. So the standard error of the difference is equal to what? We're going to take the square root of this, 4 over the square root of 19 squared, plus the square root of this one squared. So that's 3 over the square root of 15 squared, right? So what do we get? See, this is 16 over 19, and this is 9 over 15. So it's just easier to do those calculations for me, right? Just easier for me. And when I did that, I got 1.2. If you want, you can just calculate this out and then divide by the square root of n if you want to do it that way to keep it there. But this way is just easier calculations for me. So I did it that way, and so then I have this over 1.2, and that's divided by 1.2, and that is equal to 1.66. So that's the T. Okay, so any questions on that? Any questions so far? All right, so now for the one-tailed and the two-tailed. All right, so how are we going to do this? All right, so let's do we'll do the two-tail and the one-tail. All right, what are the p-values for both? Well, really only have to look up this right here. This is our T. So, and the degrees of freedom is 15. And degrees of freedom is equal to 15. So we're going to look up 1.66. That's really close to, for a one-sided Z, that's going to be significant. But on a T, what do? We're going to look at the, whoops, here's 15 degrees of freedom, right? And so now 1.66 is between 5 and 10 right here. So it's between 5 and 10. So the p-value is between 5% and 10%. Let's use the p-value calculator to see what it is exactly. Okay? So let's go to our p-value calculator and look. Okay. All right, so you want to go to the t distribution, and it has 15 degrees of freedom, and we said 1.66. All right, now we could do for one tail. What do we get? For one tail, we get 5.88. So 0, right? 5.88. Let's write that down. So for one tail, p-value one tail is 5.88%. And let's look at the two tails. And for two tails, we get 11.77. Okay. Does that make sense? It's twice it. Now, all right, so now let's go back to the document camera and write that down. Okay, so for the two tail, we got 11 what did we say, 77%? And then for the one tail, we got half that. So we got 5.88%. All right, now let's draw the picture. So the two tail, so there's 5.88% and 5.88%. So you get twice as much for the two-tailed. Does that make sense? Now what about a z-test? What do you think? Do you think the z-test, p-values with the, if you use the z-test, your p-values for z-test are smaller. Why? Because the tails are smaller. So if we have, and we'd also get a slightly larger, we wouldn't be using as much error here, so you'd get a slightly larger statistic here. So our statistic would be slightly larger, plus the tails, the big difference is that the tails are smaller. Okay? So, okay, so here's an example where, okay, so we don't reject the null, but if we used a z-test, we would get something less than 5% for the one-tailed test. So there's where people might like do some data snooping. All right, any questions on any of this? Yes?
Can our sample size be different at the beginning?
Can your sample size be different? Sure. We had a different sample size here. That's why we adjusted two different standard errors. The bigger your sample size, you're going to have, for the same SD, you'd have a smaller standard error. Usually people optimize experiments by, if you make the sample size the same, it reduces, like if you divide it up equally, then it reduces your standard error. It's more optimal to do that, to make them equal. This probably just happened for some reason, they just had, maybe right at the beginning they couldn't get the people or something happened. Usually they try to make them this is pretty equal. When possible, they try to make them equal. Any other questions? Yes?
This will be on the homework today.
The two samples will this be on the homework? That's a good question. The two samples t-test, I don't think I'm not sure. If it's not on, gosh, I don't know. Should we look?
I signed
It is on the homework? Oh, it's a good thing we covered it. Yes, it is on the homework. But is it, think of it, don't get hung up with all these calculations here. Just know you're doing exactly the same thing. The only difference here, if you want to just use it, is just to divide your Instead of dividing by the square root of n, divide by the square root of n minus 1. Okay? That will increase your standard error a little bit. That's basically what this adjustment does. When we do this adjustment, if we were going to do it from scratch and take a standard deviation, what we would do is get all those for using SD plus. To get SD plus instead of SD, we just take all our deviations from the mean, square them, add them up, and instead of dividing by n, we divide by n minus 1. That's what SD plus is. But you can do it at this stage just as easily. It's fine. And it's probably easier to do it there because of it's more accurate because you won't lose all the rounding business. So any other questions on any of this? The one-sided versus the two-sided? Is this on the homework this isn't on the homework that's due tonight, it's on the homework that's due Thursday night, right? It's not on the homework that's due tonight. I wouldn't do that to you. No, it's on the homework that's due Thursday night. You already did the homework, that's why you don't, yeah. It's on the homework that's due Thursday night.
And when will this video lecture be posted?
This video will be posted in probably a few hours. Usually it's posted around 12:30. Any other questions? I love that you're asking questions, especially because now I don't have to go back and correct that mistake. I would have looked tonight, that mistake you got. I would have looked tonight, and then I have to put in one of those, like, you know, things saying, no, this should be something else. And so these typos, we all make typos, and I really appreciate you catching them, like, in the moment. So anybody who does will get an extra credit point on their exam. So come up to me after class, whoever got it this time. It's fun for me, and it's more fun for you. It makes it more like a game. It makes it more exciting. Otherwise, we just both space out. All right, so I think that's it. Finally, a few minutes early, you're getting out.